about this concept.
Yeah, all right. Thank you so much, Janosch, Palash, and everybody for organizing this Hungarian seminar, and it's a pleasure to be here. And so let's kickstart the first seminar of this season. So the idea for this talk is that I want to talk about implementation of a certain machine learning algorithm called support vector machines using the machinery of reaction networks. So that's the idea for the talk. And this is joint work with Amay Chaudhary and Jashin Jin. All right, so let's get started with the talk. So, uh, so the talk will involve the following topics. I will start with some fleeting introduction to reaction networks, which I guess most of you are aware, but for completeness, let me give you some introduction to reaction networks. Then I will talk about support vector machines, which are supervised machine learning algorithms. And then in the next three, four kind of sections, I will talk about how to implement support vector machines using reaction networks. And in particular, we'll be using certain modules and what is called as the dual rail encoding. And we'll be implementing two things, the feed forward module of SVM and the back propagation module of SVM. And in the end, I will summarize some results that we have got by using CRNs to implement SVMs. All right, so that's the broad outline of the talk. So let me get started with the talk. So I mean, as as many have said before, cells is a tumultuous environment with many reactions and things which are going on together. And standard deterministic mass action kinetics says that the rate at which a reaction occurs is proportional to the concentration of the product of reactants, right? So the rate at which a reaction occurs, the rate can be written as K times the product of concentration of reactants. So for example, the rate of a reaction x1 plus x2 going to x3 is of the form K times x1 times x2, where x1 is the concentration of capital X1 and x2 is the concentration of capital X2. And given this usual common frame of uh, modeling mass action kinetics, you can also think of how to represent a reaction network, right? So you can think of a reaction network as a Euclidean embedded graph, G equals V. So this is notation that people have been using for a while now, where V is the set of vertices and E is the set of edges, right? So for example, here is a reaction network with the following vertices, 0, 0, 0, 2, 3, 2, which is, I guess, this one, 3, 0, 1, 1, and 2, 1, right? And essentially, you have five reversible reactions and two irreversible reactions in this network. So the basic idea being that you can always use geometry to represent a reaction network. So each reaction is a vector that is embedded in Euclidean space, and you can think of the span of those reaction vectors to sort of do the linear algebra on the reaction network. So, of course, so this we'll call this an E graph or the Euclidean embedded graph, and we will denote by bold K to be the vector of rate constants, right? We will call GK a mass action system, and its associated dynamical system is given by this, which is the sum of rate constant times the monomial times the difference of the rate vector, right? And where we define this monomial x to the power y as x1 to the y1, x2 to the y2, so on up till xn to the yn, and x is the vector of concentrations of the chemical species in the system. Okay? And as is usual, the stoichiometric subspace is the vector space spanned by the reaction vectors. So S is the span of y prime minus y for each y to y prime in the set of edges. And for any positive vector x0, the set Sx0 will denote the affine translate of this stoichiometric subspace intersected with the positive orthant, right? So it is the affine invariant polyhedron. And for mass action kinetics, this is invariant, right? So once you stay inside this set, once you are inside this set, you remain in this set forever. All right, so this was some basic introduction. So for example, you can think of this reaction in two-dimensional space with uh, you know, with these many species and these reactions. So you have this reaction going from y1 to z1, which is 1 comma 0 to 2 comma 0, y2 to z2, which is going from uh, 1 comma 1 to 0 comma 2, and y3 to z3, which is going from 0 comma 1 to 0 comma 0, right? And as I said, that given a rate constant vector, the associated dynamical system is given by k1 x1 times the rate vector plus k2 x2 times this rate vector, which is minus 1 1, which is this one going from y2, plus k3 x2 times 0 0 comma minus 1, which is this rate vector that comes from y3, right? So essentially, associated with every reaction network, you can write down a mass action system generated by this, right? And we are going to use this system to kind of implement some nice algorithms in machine learning. So that's the plan. All right. So let me introduce another piece of notation, and that notation is the notion of catalytic species, right? So in what follows, I'll be using catalytic species. So let G be a reaction network with reactions R1 to RR, where each reaction has this form: alpha IJXI to beta IJXI. A species Xi is said to be catalytic if the number of species in the reactant and product complexes remains the same, but this should be true for every reaction, right? So
I'm sorry, Abhishek, but I would call this a catalyst. And I would call a reaction step catalytic. An enzyme is a catalyst.
Yeah,
At least this is how it is used in chemistry. You can use anything, but okay, you can go on.
Yeah, no, you're right. You're right. It should be called catalyst, but I kind of use it interchangeably. But you're right. I mean,
Okay.
yes. Yeah. So you can call the reaction network catalytic if that's preferable. So, but essentially the basic idea being that the number of species remains the same, and we are going to use catalytic species throughout the talk to build on modules that can implement machine learning algorithms. And of course, it is non-catalytic if it is not catalytic, right? If there exists a even if there exists one reaction, right? You don't need this to be true for all reactions. To be non-catalytic, it suffices to only find one reaction for which the corresponding alpha ij is not equal to beta. All right. And so now that we are acquainted with much of the terminology, we can now move on to so the basics of machine learning tasks, which is support vector machine. But before we go there, let me show you an example of catalysts and non-catalysts. Right. So in this network, we have three species, and among those, X1 and X2 are non-catalytic because they don't appear both on the right on the product as well as the reactant with the same stoichiometric coefficient. But X3 is the catalytic species. All right. So this is an example that illustrates both sides. And what I want to now turn my attention is that, I mean, using molecules to perform computation, the idea of using molecules to perform computation is not new, right? It goes back many years ago. I mean, one of the first instances to do this was Len Adelman, who demonstrated in 1994 that one can solve the traveling salesman problem using DNA strands. So what you see in his hand are DNA strands, and you could do strand displacement reactions and polymer exchange reactions to actually solve an NP-hard problem called the traveling salesman problem. So the Hamiltonian path problem, right? So using molecules to do computation is, this idea is not new. It has been there for about more than 3 decades ago. And a recent paper of mine with David Anderson and Badal Joshi uses this, kind of furthers this by using reaction networks to implement neural networks, the feed-forward part of neural networks, right? And also there are other works by Eric Winfrey, William Poole, Andres Ortiz Munoz, and Tom Ulrich, which have used reaction networks to build chemical Boltzmann machines, right? Can you build kind of Boltzmann machines where you can model probability distributions, right? So not just do deterministic stuff, but you can also use uh, reaction networks with clamping of species to actually model conditional probability distribution. So that's what they do in chemical Boltzmann machines, right? So all this body of work exists, and this work kind of takes it further one step by implementing a different algorithm. So this brings us to the main idea of the talk, which is the support vector machines, right? So before we go to a definition of a support vector machine, I just wanted to spend a few minutes on explaining what kind of algorithm is a support vector machine, right? So machine learning has two kinds of algorithms. One is supervised learning algorithms and one is unsupervised learning algorithms. The focus of our talk today is going to be on a supervised learning algorithm called the support vector machine. And the idea in supervised learning is to essentially train an algorithm on a known data set to predict output on new unseen set of data, right? And in particular, one problem that this can solve is classification, right? So support vector machines are going to help classify data in the right class. So let's have a look at how support vector machines can achieve this, right? So just to put into historical context, support vector machines are supervised machine learning algorithms. They were invented by Wapnick and Siegelman uh, many years ago. And the idea is to construct a hyperplane in RD, in Rn, that separates data into classes. And the key point here is that it should maximize the distance between itself and the nearest data point. Okay, so I'll come to what it means by nearest data point, and I'll explicitly tell you what exactly it means to separate data and stuff. But to give you a rough intuitive definition, right? Idea is to generate a hyperplane that separates data into classes, right? So for example, what you see in the figure are red dots and blue dots. The red dots represent one class, the blue dots represent another class, and we can assign a class label to each of them. So the red dots can be labeled as +1, the blue dots can be labeled as -1, and we want to know what is the best possible hyperplane that can separate this, right? So that's a classification task. So we need to know, is there a hyperplane in higher dimensions that can effectively classify data? Of course, you cannot always do this. I mean, data has to be linearly classifiable for there to exist a hyperplane that can separate data into two paths like this. But let's have a look at it in more detail, right? So what are the exact conditions required? So for example, imagine that you have data which is scattered like this, right? Black dots here, white dots here. And imagine that there are three hyperplanes here, H1, H2, H3. And as you can clearly see, H1 and H2 are not really effective in separating data, right? Because they don't really, I mean, H2 does separate data. H1 is not really doing a good job because it's keeping one color points on one side and also the same color points on the other side. H2 is still doing a decent job because it's separating data, but it's too close to some of those points, right? Can you come up with a very good hyperplane that maximizes the distance between the nearest points, right? So if you see this hyperplane H3, then, and if you measure the distance between the nearest point, which is this black point, and this white point, this hyperplane is kind of the optimal hyperplane, right? And question is, when can we find this hyperplane and how do we find this hyperplane, right? And of course, the eventual question is going to be, can you build a reaction network scheme? Can you build a chemical soup that can actually build this hyperplane? That's the eventual question that we'll answer, right? So here is the more mathematical structure of the problem. So let's say that we are given a data set xi, yi, where xi are feature vectors, which means xi in RD can denote, for example, the height, weight, or let's say other features of a human being, for example, height, weight, and uh, body mass index, or for example, other features that you can think of. And yi belongs to 1 or -1. Let's say a person is healthy or unhealthy, depending upon what those parameters are. Suppose you have his body mass index is less than a certain number, then, and if height is and weight is less than a certain number, then the person is healthy. And then we classify that as 1. If it's unhealthy, we call that label as -1. All right. So uh, these will always deal with binary class labels. And the goal is to find a weight vector W such that it maximizes the distance of its nearest point for each class, and a bias B, because of course this hyperplane does not pass to the origin. It's an affine translate. It's a translated hyperplane, such that the following is true.
I'm sorry, Abhishek, I don't understand. W doesn't depend on B.
No.
Then why do you write my minimum over W and B?
Well, I want to find both W and B that minimize the distance, that minimize this.
But then this is not the distance. Then W square is not the distance.
Yeah, there is something more. I didn't write the whole distance formula. Yeah.
Okay, thank you.
There is something more. Yeah, sorry, there's a typo here. There's something more than
Okay,
just.
thank you.
Yeah, you're right. Yeah, I see what you mean. Okay. So that maximizes the distance between this. So what it means is that the label is +1 or -1. So Wi, the ith feature vector, times this number, which is W dot with xi plus B. This must be greater than or equal to 1. So for example, Wx plus B is, let's say, positive, Yi is +1, then together the dot product is greater than 1. And if it's negative, then the dot product is, if both are negative, then they're still classified correctly, because the point lies on the other side of the hyperplane. For example, here, right? If this point lies on the other side of the hyperplane and its label is -1, then both these terms are negative, -1 and -1, and then the product is still positive, greater than 1, right? So we want to classify points correctly, and we want a weight vector that maximizes the distance of its nearest point, and the distance is given by 2 by the distance is given by 2 by norm of W plus something. And that's why maximizing the distance means minimizing the norm of W square, right? Subject to the constraint that the training points satisfy equation 1. So we want to find, the optimization problem is defined as this. We want to essentially minimize maximize the distance is the same as minimizing the norm of W square. We want to minimize the norm of W subject to the fact that you have this this optimization problem, y times Wx plus b is greater than or equal to 1. So how do we solve this, right? So the way to do that is using gradient descent, right? So we can do an iterative training with error-driven update. That's the standard jargon in machine learning. So given data points, we define a regularization parameter, which is used to do kind of iterative gradient descent, and a learning rate, which tries to update both the weight and the bias in a certain fashion, right? So the idea is to do the following. The idea is that, let's say we initialize W as something and B as something. What we do is compute the decision function for each data point, xi, yi in the data set. So f of xi is W times x plus B. And if there is misclassification, which means that if the dot product of y with f of xi is less than 1, then you can show that by calculating suitable gradients, you can essentially change the W and the B vector in the following fashion. So let me explain. Given an original W vector, you change the W vector by going W minus the learning rate times the regularization parameter times W minus yi times xi. And the bias is a number, note, W is a vector, but bias is just a scalar, is updated as the bias plus eta times yi. So if there is misclassification, you update W and B in the following way. And you can derive these equations by using Lagrange multipliers, right? So you basically use this optimization problem with these constraints. You form a Lagrange multiplier system, calculate the gradients, and what comes out is this. Okay. And if there is no misclassification, then we have to do something special. If there is no misclassification, nothing happens to the bias. You can show that nothing happens to the bias, but the weight is only changed by weight minus eta times lambda w. So note this crucial difference that if there is misclassification, there is this extra term in the w update, which is eta times y times x in addition to eta times lambda times w, right? And so we need to do different things for different scenarios, right? So if we need to check whether there is margin violation or misclassification, then you need a different way to update the weights and the bias. And if there is no misclassification, then you need to do something else to the weights and the bias. All right. And then once you have got this, okay, so once you do this iteratively for many iterations, then once you have got this optimal W and B, question is, can you frame a decision rule for this? So after training, the classification decision for a new point x hat is determined by whether this is greater than 0 or less than 0. So let's say I take this W and B that I have found using this update rule that I have shown you after many iterations. I take this new data point x hat, and then I ask whether this f of x hat is greater than 0 or less than 0. If it is greater than 0, then my new point has label +1. And if it is less than 0, then my new point has label -1. All right, so this is how you do training and decision tree. So this was the essence of SVM. I mean, of course, there are many variations. So this was just the start. This is the most rudimentary version of SVMs. There are, of course, other things like soft hard margin SVMs, soft margin SVMs, and other variations, which I won't go into in this talk. But this is the basics of SVM, support vector machines, right? So the idea is that by the way, this only works if the data is linearly separable, right? So for example, what I wanted to say, only if the data looks like this, can you actually solve the problem using SVM? And if the data is scattered, for example, there are lots of black colored balls on the other side and white colored balls on the other side, and they're mixed, then you cannot use this to solve using SVM, right? A prerequisite for using SVM is that the data is linearly separable. So this was some introduction about SVM. Now question is, can we use reaction networks to implement this, right? So of course, I mean, you can do this in silico, right? You can write a program in Python or C or MATLAB or your favorite programming language that implements this. You take some data set, known data set from some resource, you write an iterative update code that updates the weights and the bias and find the optimum weight and bias. But what we are interested in doing is molecular computation. Question is, can you design a reaction network that does this for you, right? So without having to write a C program, without having to write any program in any programming language, can you cook up chemistry that automatically does this for you? So this is what we are going to focus in the next part of the talk. And we are going to develop a reaction network scheme for the individual submodules that will be used for implementing two things. So we'll be using what is called as the feed-forward module and the backpropagation module. So let me explain what does feed-forward mean. Feed-forward means that we need to compute this quantity y times wx plus b, right? Computing this quantity and comparing it with 1 is what I call the feed-forward module, right? So this equation 1 that you see, which is this constraint, is what I call the feed-forward module. And these update equations is what I call the backward module, the backpropagation module, right? So we are going to design reaction networks that implement both the feed-forward module and this backpropagation module. One point that needs explicit mention is that in a physical setting, concentrations of species is always non-negative, sorry. However, data points and weights can be negative. So what do we do, right? So how do we represent negative data points using species, because concentrations of species can only be non-negative. So what do we do, right? And for that, we use a trick called the dual rail encoding. In particular, it means that for any real variable, any zeta in R, we take two species, zeta plus and zeta minus, with non-negative concentrations, right? Because concentrations of chemical species can always be non-negative, such that the difference of zeta plus and zeta minus will represent the real value zeta. So let me try to explain what this means. This means that, let's say you give me a number -3, then I will take two numbers, zeta plus equals 2 and zeta minus equals phi, both positive, such that 2 minus phi is -3. And I will cook up reaction network that gives me this value 2 and phi. And then remember that 2 minus phi is actually giving me something negative, right? So this needs to be taken care of in everything that I do in the next half of my talk, right? Every module, every reaction that I now will discuss will always be taken considering the dual rail encoding, right? So this is important to kind of mention this at the beginning. All right, so we use certain basic modules and certain more sophisticated modules for doing this task. And some of these are already known before, and some of these are new, and we kind of have to use a combination of them to accomplish support vector machine, accomplish implementing support vector machines. So the first module is the addition module. So the addition module has three reactions. A goes to A plus C, B goes to B plus C, and C goes to the empty set with all reaction rates set to 1. And as you can see, you can write down the ODE for this, and the ODE is A plus B minus C. And as you can see, if you let this evolve for a long time, the steady state concentration of C is given by the sum of A and B. So you can use this module to add two numbers. Of course, as I said, you need to use this in conjunction with dual rail encoding. Okay. And the next module is the multiplication module, which means can you use chemistry to multiply two things? All right. So this consists of two reactions, A plus B giving you A plus B plus C, and C giving you empty set. Right? Then the dynamics associated with this network is given by A times B minus C. And again, if you solve for the steady state, then C is given as A times B. So you can use this module for multiply. So these are relatively simple modules. And now here is a slightly, this is a slightly sophisticated and complicated construction. It's called the comparison module and approximate majority. So the next two things are going to work in tandem. And the reason I need it is because, please recall that I need to compute this quantity, W times X plus B, and I can do that using multiplication and addition. But now I want to compare this Y times WX plus B with 1. And how can you teach a reaction network to compare two numbers and kind of act on the result of that comparison, right? So if it is greater than 1 or less than 1, so if it is greater than 1, then it's classified correctly. Then I want my reaction network to do the following, this bottommost thing. But if it's classified incorrectly, I want my reaction network to update weights and a bias in a certain fashion. So how do you teach a reaction network to do this? This is somewhat complicated. And for this, we need to use two things in combination. One is called the comparison module. And this module does, what it does is it takes the inputs X and Y, and they're assigned to something called as the flag species XGY and XLY in a normalized fashion. What I mean by this is I have this network with XGY, XLY, and X. And of course, there are some reactions that go to the empty set, which I haven't really put on this slide. And to normalize value within the range, we set the initial concentrations of XGY and XLY such that they sum to 1. Right? So these new flag species, their concentrations are set such that they sum to 1. And you can show that at steady state, their concentrations are related as follows. So at steady state, you have the concentration of XGY is X upon X plus Y, and XLY is Y upon X plus Y. And now what we are going to do is crucially use this in conjunction with another slightly complicated module, which is the approximate majority module, to compare two things and do something that the SPM wants to do, right? So let me explain how. So here is a slightly more complicated module. This is an approximate majority module. And this module, what it does is it's used to detect which flag species is in majority using this network. Of course, I have not shown you the whole network, but this is the essence of the network. B is some intermediate species that you need. And you need to use this approximation and comparison module in tandem, right? So assuming that the normalization step in comparison module has already been performed, which means this xgy and xly have been normalized to x upon x plus y upon and y upon x plus y. What this does is that it takes this xgy, xly, b to the state 1, 0, 0. So it assigns xgy to 1 and xly to 0 if xgy was greater than xly of 0, right? So if this x was greater than y, then it assigns this xgy 1. So it detects which is in majority. If the species x was greater than species y, which means this xgy at steady state was greater than xly at steady state, it assigns this xgy to the state 1 and it assigns xly to the state 0. So this is an indicator. So for an experimenter, if you observe that xgy goes to 1 and xly goes to 0, you know that x was in majority. And if the other thing happens, which means if it's assigned to 0, 1, 0, then you know that xgy was less than xly, and y was in majority. So we need to use these two things in tandem to teach a reaction network to compare an inequality of this kind. So what we need to use this module is to, what we're going to do now in the next steps is to use this to teach a reaction network to multiply these things, add these things, which can be done by this addition and multiplication modules. But now do something smart. Compare this with one and do something more depending upon the result of that comparison. So that's what this comparison and approximate majority module is going to do. And then we have I will have 2 or 3 more modules, and then I will go on to the main procedure. So the loading module simply loads the species A into B. So this is just saying that can you copy species A into B? And that's just these two reactions. A goes to A plus B and B goes to empty set. Similarly, we can also do subtraction, right? So this subtraction is a bit more it's kind of soft subtraction because it computes kind of max of A minus B and 0. So if it's A minus B, then the steady state is, if it's A is greater than B, then the steady state of C is A minus B. And if A is less than or equal to B, then the steady state of C is just 0. So this is the soft subtraction module. And now all this is fine. So this is basic machinery that we have built up for building SVMs. The next thing that we need to do is to do timescale separations, right? So what we need to do is we need to be very careful that we need to do W times X first, then add B first. This can be done together. But once WX plus B is computed, then multiply by Y. And once you multiply by Y, then compare with 1. And once you compare with 1, depending upon whether it's less or greater misclassification, then you do these weight updates, right? So there is a sequence of steps that you need to do. And to do timescale separation, what we use a trick is called oscillation molecules with doping, right? So there is a trick in chemistry that is this oscillation molecules, which is this sequence of reactions given like this. And the idea is that if a reaction contains an oscillation molecule of index O1, which is where I is less than J, then the reaction containing the oscillation molecule will be executed before the reaction containing the oscillation molecule OJ. So this is just some snapshot of the oscillation molecules. I mean, the network is much bigger than this, but I'm just telling you what kind of things we are using. But there is a small problem with this. If you use oscillation molecules just as is, they eventually die out after a certain time because they are never perpetual. And to make the oscillation molecule perpetual, we incorporate what is called as a trick called doping. So we introduce a new variable D, these reactions that you see down, which interact with this n-way oscillation molecule. And this addition of this extra molecule D ensures that these oscillations never die out. So you get perpetual oscillations that always remain for all periods of time. And using these tricks, we are now ready to implement both the feed forward and the back propagation module of SPI. Right? So here is the trick. So what we want to do is we want given an input sample and an associated label. Our objective is to determine whether W times Wx plus B is greater than 1 or not. Can you cook up chemistry that actually accomplishes this? So here is step one. Step one is calculating W times X, right? So you can use the multiplication module to do this. You need to calculate W times X1 plus W2 X2 plus W3 X3 WD XD. And you can use this multiplication addition modules to accomplish this. So this is just using knowledge of previous modules that we have seen. The next thing is to compute the sum plus this bias B, right? So we need to compute basically this term, which is W times X plus B. So it's W1 X1 plus W2 X2 plus Wn Xn plus B. And that's what this step 2 is doing. It's computing this P with this intermediate molecule B such that the resultant is Wxi plus B, the sum of all such Wxi plus B. So this is done in the same oscillation step. So this is done first, then this is O2 is done later. So in the next oscillation step, we do this. And now what we do is in the next oscillation, we multiply this result with Y, right? Because eventually what we want is to multiply Y with Wx plus B and compare the result with 1. So in this third time scale step oscillation modulo 3, we multiply by Y and store the result in Q. So far so good. And now comes the slightly non-trivial step. How do we compare Q to 1? And here we use the comparison and approximate majority molecule. Right? So we introduce the catalytic species K with 2 flag species, as I have shown before in the comparison module. We set the concentration of K to 1, and we set the flag species such that their initial concentration sum to 1. And now using the comparison module, we can force this flag species KLQ and KGQ to take these values, Q upon Q plus 1 and 1 upon Q plus 1. And now what I'm going to do is compare Q with 1. That's what I wanted to do, right? Because Q is this quantity, Y times Wx plus B. I wanted to compare Y times Wx plus B with 1. And this comparison module is essentially going to do that. I'm going to take this Q in this next oscillation molecule and compare Q with 1. And the approximate majority molecule is going to tell me whether it's greater than 1 or less than 1. So now, again, as I've shown before in step 5, the fifth oscillation molecule, I'm going to use the approximate majority and introduce again flag species such that if Q is greater than 1, then KLQ converges to 1 and KGQ converges to 0. So as a proof of correctness, if I see that if KLQ converges to 1, I know that Q was greater than 1 and Q is this value, Y times Wx plus P is greater than 1, which means my point was classified correctly. So this using this comparison and approximate majority module in tandem is going to teach my reaction network to compare things and do things in a certain fashion. So what do we do? So once we know if it's greater than 1, we need to do the back propagation module, right? So here we need to be careful. So again, let me recall the back propagation module is that if the point is misclassified, then you do a different update on the weights. And if the point is classified correctly, then you do a different update on the weight. So, and note that this term n lambda w is common in both update rules of the weight. The only extra term in the update rule of the weight is eta times y times x. This is the only thing extra if the point is misclassified. So let's see how you can do the back propagation. So to do the back propagation, I first use again the multiplication and some module to calculate this term, the learning rate times the regularization parameter times the weight W, which is this term, n lambda W, this term that you see here, n lambda W, that's this term that is being calculated in step 1. Of course, this needs to happen in the next oscillation step, O6. So what we have done so far is just in the back propagation step, just calculate n lambda W1, which is just this term. And now in step 2, we introduce two species, X, Y, and S, whose steady state concentrations represent the quantities, this quantity, which is eta times xi times y times this kgy, right? So because this kgq is going to be 1 or 0 depending upon whether our comparison in the previous step was 1 or 0, right? Recall that kgq is a switch. So if in the previous step our point was classified correctly, then kgq is 1. Otherwise, kgq is 0. So this kgq species is going to be used here to basically now connect with the comparison that was made in the previous module, right? So what is being done in O7, the 7th oscillation module, is compute this term, eta times x times y and eta times y, right? So these two terms, eta times x times y is this last term in this update rule, and for the bias, eta times y. So these two terms are going to be now calculated. So this is the first calculation in step 1. And now we update the weight using the subtraction module, right? We haven't yet used the subtraction module, but now if you look at this carefully, you need to subtract something from the weight. You need to do W minus eta times this. And then we can use the subtraction module to update the weight. And this happens in oscillation molecule O8, right? So use this H molecule and the V molecule to basically update this. And again, we use these species are used as catalyst here. W and R are used as catalyst here, and we can accomplish the weight update. And similarly, you can update the bias, right? So recall S was the update in the bias, and now you can use this reaction network to update the bias according to the rule that you have. For correct classification, there is no update to the bias, but for misclassification, you need to add this S term, right? So that's the idea. And once you do this, you can now load everything into B. You can now club everything together and essentially update the whole weight and biases. So this is the loading module, the sum of everything that has been updated till now. You update everything, the weight and the bias, and this is being done by the loading module, right? So what we have essentially achieved is we have used combination of basic arithmetic reaction modules and some complicated things, which is approximate majority and comparison modules and timescale separation using oscillation modules with doping to successfully simulate or mimic a support vector machines. Let's have a look at the results. So let's say that we use all these reaction networks and all these timescale separation techniques to sort of implement these formulas. How do these formulas compare with reaction network implementation? So that's the next thing. So as you can see, we took some data and we took two parameters, W1, W2, and a bias just for testing. And these are the values that you see. So the actual value is 0.2352. The predicted value is 0.2356 using reaction network. The middle column is the one that is being calculated using our reaction network implementation, and they are fairly good with fairly robust and low values of error. And you can also see this as a function of plot. So these are weights W1 and W2 and bias C. Figure C is bias, and figure A and B are weights. And you can see weight 1 and weight 2. The blue line is the actual line which you can calculate in silico by programming. And this dotted red line is the line that has been simulated using CRNs, using all these modules. And they are fairly in agreement with some errors within tolerance. And finally, figure D is showing something interesting. Figure D is showing the actual SVM, right? So the actual SVM is this dotted blue line that separates the two data points. And what we get using reaction network is this black line that you see there. So, I mean, there is some difference, and that difference arises due to numerical inaccuracies of simulating ODs and steady states and floating point numbers, but it's fairly close to the actual value of SVM, right? So I think I have come to the end of my talk. So to sum up, what we have done is use basic arithmetic and combination of several modules and knowledge of some reaction networks to successfully mimic uh, a supervised algorithm, a supervised machine learning algorithm called support vector machines. And here are some references. So these things about Vapnik, Cortez, and Luca Cardelli, and cell cycle switches that computes approximate majority. So all these are there in other resources for you to read. And with that, let me end my talk. Thank you so much for the attention.
Thank you, Abhishek. Questions and remarks? I have a small question. You have shown errors, but it is not the difference between the actual value and the predicted value.
Yeah, it is some other. It's not the absolute error. It's some other error, mean square error, or some other
Okay,
error. It's not the.
okay. Thank you. So it was
So,
good.
Abhishek, can you comment on the next page, I think 38. So what caused the difference between the dashed blue line and the black line?
So, I mean, the thing is that there are numerical inaccuracies when you simulate ODs and do timescale separation, right? They do not occur exactly. Like the values that you get are close, but they're not really exact, right? So you see that these weights and biases are similar, but there is some difference between them due to numerical inaccuracy. So when you simulate ODs, do steady state calculations, and do time scale with time scale separation using oscillation doping, you get numerical inaccuracies, and they pile up, right? So you have about 10 oscillation molecules, and each step, even if there's an error of 0.01 in each step, this piles up with every multiplication, addition, comparison, and everything that you do. And together, when you combine all of them, that results in somewhat considerable error.
I see.
Do you have any feeling, Abhishek, for how sensitive these networks are to perturbations in the rate constants that appear in these networks?
So at the moment, I have put all rate constants to 1. I have not really changed anything. Like they are set to 1 at the moment. But I think what would be interesting to explore is how do these behaviors change with tweaking the rate constant? Is this what you meant? I mean, is
Yeah, I
this?
mean, I guess I imagine that if we try to implement this in a cell, it would be very hard to precisely sort of fine-tune the environment of the cell to make sure that all the rate constants are exactly 1. So they would maybe be 1.2 or 1.001 or something like that. And how much would
Yes.
that mess up
And
the
there is another
output?
point that the reactions are very high order here. So
That's
there
also
were
true.
reactions of order 5 or 6, I don't know. This is not so easy to realize in real chemical systems.
Yes, so that you're right. So this actually doing it in practice is going to be not so easy. That's
Right.
you cannot really fix, as Oscar said, values, but
But
in
maybe
principle,
there is some
yes.
robustness to such changes. Like it would be nice to know if it's very sensitive to the rate constants or if there is some sort of robustness to small perturbations in the rate constants.
I see. Yeah. Yeah, good point. And I think it would be good to explore this. Yes.
As to the high degree, uh,
Well,
Tomislav
yeah.
Presa was able to construct reactions of lower degree, which are equivalent to reactions of higher degree in a certain circumstance. No, not in this case. Maybe he has some idea which would be useful here to decrease the degree of the reaction steps.
Okay. Yeah, nice talk, Abhishek. Yeah, you can use some of the frameworks that. Can you hear me?
Yeah, please go ahead.
Yeah, you can use some of the frameworks in one of these papers that I developed. The only cost, well, quote unquote, only is that you have to introduce additional timescale separations. So your algorithm, you know, when you implement this in chemistry, you would have to have further faster species, which, you know, it can become infeasible, but it is doable. You can break it down into bimolecular reactions systematically.
I see. So you mean for each module you do this, but again, within each module you create extra fast and slow species and do this. Is this what you mean?
Yeah, so each reaction that has more than 3 reactants, 3 or more, you can break it down into 3 or more reactions that are at most bimolecular. Now I would have to look precisely at the modules. You can sometimes reuse the auxiliary species for multiple reactions and multiple modules. So there is some scope to optimize, basically to reduce the number of extra species you have to introduce, but that depends on precise details of your network. So I would have to look precisely. But yeah, you would apply it to each individual reaction, basically. At the worst case, and in the best case, you would find smarter ways to kind of approximate a few reactions in parallel, or many, or perhaps many.
All right. Yeah, good point. And so you have this in one of your papers, or I mean?
Yeah, I'm happy to send you the link.
Oh yeah,
I'll email
sure.
you.
Yeah, please email. Yeah.
It also works at the stochastic level if that's of any relevance.